Hello everyone and welcome back to the next lecture of control systems. In this presentation, we will take a review of Laplace transform. So let's get started. The Laplace transform play a very important role in the modeling of control systems because when we do the mathematical modeling of control systems, we get differential equations. And the Laplace transform converts the complex differential equations to simple algebraic equations. Taking this motivation, we can start with some of the important points of Laplace transform. Laplace transform is the tool to represent the frequency domain of a time domain function. So we can see that if we have a time domain function and we want the frequency description of that function, then we can use Laplace transform. Laplace transform was given by Pierre-Simon Laplace, who was a French mathematician and an astronomer. Moving on to the next point, the Laplace transform is an integral transform. The general integral transform is given as g of alpha is equal to the integral from a to b f of t multiplied k of alpha comma t dt. In this expression, g of alpha is the function of alpha and this is the output. F of t is the function of t and this is the input. And k of alpha comma t is the function of both alpha and t, and that's why we call this function as integral kernel. So we can see that the integral kernel is a function of both the input variable and the output variable. Moving on to the next point, the Laplace transform of any function f of t is represented as Laplace of f of t and is given as f of s. So the Laplace transform of any function f of t is given as f of s is equal to the integral from minus infinity to infinity f of t multiplied e to the power minus st dt. In this expression, s is equal to sigma plus j omega. Comparing this expression with the general integral transform expression, we can see that f of s is the function of s and this is the output. F of t is the function of t and this is the input, and e to the power minus st is the function of both s and t, and we can call this function as the integral kernel. And this is the Laplace transform expression which is used to convert the time domain function to a frequency domain function. In this expression, s is equal to sigma plus j omega, in which the sigma is the damping factor of control system. The stability of control system depends upon the damping factor, and the omega is angular frequency. So now we are done with the expression of Laplace transform. We will now use this expression to convert a standard time domain signal to its frequency domain. Let's take an example. Find the Laplace transform of unit step function ut. Moving on to the solution, we are given the value of f of t as equal to ut and we need to find its Laplace domain. From the definition of unit step function, we can say that unit step function is equal to 1 when t is greater than 0 and it is equal to 0 when t is less than 0. We can also plot this function graphically like this. Whenever t is greater than 0, the value of function is 1, and when t is less than 0, the value of function is 0. So on the right half plane, the value of the function is 1, and on the left half plane, the value of the function is 0. We will now calculate the Laplace domain for this function. The expression for finding the Laplace transform is f of s is equal to integral from minus infinity to infinity f of t multiplied e to the power minus st dt. Now we will replace this f of t by ut like this. From the definition of ut, we know that it is equal to 1 when t is greater than 0 and it is 0 when t is less than 0. So the integral from minus infinite to 0 will become 0 because the function value is 0 in the left half plane, and on the right half plane the function value is 1. So our integral limits will change from 0 to infinite because the value from minus infinite to 0 is 0. So now we have this function and we need to integrate this function. So we know the integral of e to the power minus st. It is minus 1 upon s e to the power minus st. And we have the limits from 0 to infinite. By substituting the limits, we will have e to the power minus infinite minus of e to the power minus 0 will become minus 1. So we will have minus 1 upon s multiplied with minus 1, and this will come out to 1 upon s. So finally we have got the Laplace domain of unit step signal, and it is given as Laplace of u of t is equal to 1 over s. So this is the list of Laplace transforms of some standard signals. We have already seen the Laplace transform of ut is 1 over s. The Laplace transform of t, or we can say the ramp signal, is 1 over s square. The Laplace transform of t to the power n is n factorial over s to the power n plus 1. The Laplace transform of e to the power minus at is 1 over s plus a. The Laplace transform of impulse signal is equal to 1. The Laplace transform of cos of omega t is s over s square plus omega square. The Laplace transform of sin omega t is omega over s square plus omega square. All these Laplace transforms can be obtained by the same expression. Now this will be your homework task to derive all these Laplace transformations using the same expression. I will give you one hint for calculating the Laplace transform of these two functions, cos omega t and sin omega t. We use the complex conjugate property of sinusoidal function to calculate the Laplace transform of these two functions. We can write cos omega t as e to the power j omega t plus e to the power minus j omega t over 2, and similarly sin omega t can be written as e to the power j omega t minus e to the power minus j omega t over 2j. So these are the hints to calculate the transforms of these two functions, and this will be the homework for you. And now we will move on to the inverse Laplace transform. So as the name suggests, inverse Laplace transform is the inverse of Laplace transform. So from the Laplace transform, we can get the frequency description of a time domain function. Similarly, the time domain signal can be obtained from the frequency domain signal by using inverse Laplace transform. The expression of inverse Laplace transform is given as f of t is equal to 1 over 2 pi j integral from sigma minus j omega to sigma plus j omega f of s multiplied e to the power st ds. So here in this expression, the input is the frequency domain function and the output is the time domain function. But we will not use this complicated equation to find out the inverse Laplace transform. We will find the inverse Laplace transform by using the method of partial fractions. The method will be clear to you when we will take some examples. So now we are done with this lecture. In the next lecture, we will take some properties of Laplace transform. Thank you for watching this lecture. I'll end this lecture here. See you in the next one.